In this video, we're going to look at implicit differentiation. This is that moment in time where you're like, well, we've studied conics before, and they're smooth, they're defined. How do we take derivatives of those? Well, here's where we're going to talk about taking derivatives of conics, which are typically not functions, except for parabolas. So when you use the derivative of a complicated function, we're going to find it using implicit differentiation, and we're going to use implicit differentiation to determine the equation of a tangent line when my original equation may not be wrote as a function. As an example, a circle. So suppose we have the unit circle, which is x squared plus y squared is equal to 1. If we try to solve for y explicitly, I'd have y is equal to the positive of the square root of 1 minus x squared and also the negative. We have the top and bottom halves of the circle. Now, if I replace y with y of x, y is a function of x, then when I take the derivative with respect to x, I'm going to take the derivative of x squared with respect to x, which is just a regular derivative. And then I'm going to take the derivative of y with respect to x, the quantity squared, so dx of y squared. This allows me to use the regular chain rule. So I'm going to have the 2 come down out front, multiplied by y of x raised to the 1 power, and then multiplied by the derivative of y with respect to x, or in other words, y prime of x. So, since y prime of x is dy dx, which can be wrote as y prime, we now have the derivative of this unit circle without having to do the upper part of the circle and the lower part of the circle. And what we have is 2x plus 2y, y prime is equal to 0, which is the derivative of the unit circle. If we solve for y prime, or in other words, we're solving for dy dx, we're going to get y prime is equal to negative x over y, which holds up as long as y is not equal to 0. But at the points negative 1, 0 and 1, 0, those are vertical tangents anyways, so that makes total sense. Now, notice the derivative that we just had is in terms of both x and y. Therefore, when we need to find the slope of the tangent line, we need both x and y to substitute in to find the slope of the tangent line. So here are some problem-solving strategies to do implicit differentiation. So just take the derivative of both sides. Keep in mind that y is a function of x, which means the derivative of sine x with respect to x is equal to cosine x. But the derivative of sine y with respect to x is going to be the derivative of sine, which is cosine, times the derivative of y, which is dy dx, or y prime. I have a tendency to use dy dx because I lose my primes sometimes, so I use dy dx. That just also helps me to remind myself I need to solve for dy dx. So then what we can do is rewrite the equation so that all the dy dx's are on one side, factor that out, solve for dy dx, and now you have the derivative with respect to the derivative of y with respect to x, which will have some y in it as well. It's not going to just be a function of x. So if we're asked to use implicit differentiation to find dy dx, we're just going to use our regular derivative rules. So the derivative of 3x squared using our regular rules of differentiation, that will become 6x. Now here is a function with y. It's y, not a function, it's just y, it's a variable. So then this is still going to be 3 times 2, which is 6y. Now, because of the fact that I'm doing the derivative with respect to x, I have to do the derivative of y. Well, the derivative of y is dy dx, derivative of y with respect to x. And then this is equal to 0 because the derivative of a constant is 0. I'm asked to find dy dx, so now I have to solve for dy dx. So in other words, I'm going to subtract 6x from both sides and divide both sides by 6y. So dy dx is going to be negative x over y. And that's because I subtracted 6x from both sides and I divided both sides by 6y. Now, for this example, for B, I have to use the product rule because I have x squared multiplied by y squared. So not only do I have to do the product rule, but gotta remember every time I take the derivative of y with respect to x, I will use the regular rules of differentiation, but then I'm going to slap on the dy dx. So the derivative of 1 is 0. The derivative of 3x is just 3 plus. My u is going to be 2x squared. That means u prime is going to be 4x. My v is going to be y squared. My v prime is going to be 2y. Don't forget to slap on the dy dx. So it's going to be 3 plus my derivative of u, which is 4x, multiplied by my v, which is y squared. Plus, I'm going to have the derivative of v, which is 2y, dy, and dx, multiplied by u, which is 2x squared. Now, again, I'm asked to solve for dy dx. So I'm going to need to bring this 3 to the other side of the equal sign, so I'm going to subtract 3 from both sides. I am also going to subtract off of 4xy squared, and then I'm going to divide by 2y. So dy and dx is going to be equal to negative 3 minus 4xy squared, all divided by 2y. And that is my answer for B. Let's take a look at C. Take the derivative of both sides. I'm going to have to use the chain rule on the left-hand side because of this squared. So the derivative of the left-hand side is going to be 2x. The derivative of the right-hand side is going to be 2 multiplied by 4x squared y cubed plus 1 raised to the power of 1. Now I have to go inside this function, or this equation, or this expression, excuse me, this expression on the right-hand side. And I see, once again, I have a u and I have a v. So this is going to be multiplied by my derivative of u, which is going to be 8x, and then raised to the power of 1, multiplied by v, which is y cubed. And then plus the derivative of v, which is going to be 3y squared dy and dx, because I'm now taking the derivative of y with respect to x, multiplied by my u, which is 4x squared. I'm asked to solve for dy dx, so in other words, I am going to go ahead and, let me see, what do I want to do first? I think I'm going to divide both sides by 2. I'm going to divide both sides by 2, 4x squared y cubed plus 1, because this is a multiplier on the right-hand side. When I do that, I'm just going to get x by itself because this 2 and this 2 will cancel in the numerator and denominator. In the denominator, I'm also going to get a 4x squared y cubed plus 1, all raised to the power of 1. This is then going to be equal to 8xy cubed plus, I'm going to have 12x squared y squared dy dx. So now I'm going to subtract 8xy cubed and then divide by 12x squared y. So I have x over, I'm going to have 12x squared y squared, 4x squared y cubed plus 1 minus 8xy cubed over 12x squared y squared, which is equal to dy dx. And then, of course, I would simplify a little bit more by canceling the x's here, canceling down the 8 and 12 they're both divisible by 4, canceling down some x's and y's there. All right, let's take a look at, let me move all that stuff up and out of the way, run away. Let's take a look at D. All right, with D, I have to pay attention to what my angle is. This is my angle. So I'm going to take the derivative of the left-hand side, and the derivative of sine is cosine. So it'll be the cosine of 2x squared y cubed. Now, I have to do the derivative of my inner function. I'm going to call this u. I'm going to call this v. So the derivative of u is going to be 4x multiplied by v, which is y cubed, plus the derivative of v, which is going to be 3y squared dy dx, multiplied by u, which is going to be times 2x squared. That's just the right-hand side. On the left-hand side, I'm going to do the derivative of 3x squared plus 1, which gives me 9x squared. And I think I said 3x squared. It should be 3x cubed plus 1, and here's the derivative. Okay. Once again, since I need to solve for dy dx, I'm going to go ahead and divide both sides by the cosine. So I'm going to have 4xy cubed plus, I'm going to multiply the 3 and the 2, 6x squared y squared. I'm going to keep the dy dx in red so I can see that is what I'm solving for. And then I'm going to have 9x squared divided by the cosine of 2x squared y cubed. I'm going to subtract 4xy cubed from both sides, divide by 6x squared y squared, so I can get dy dx by itself. So dy dx will be equal to, oh, that's way far out than I needed. I'm going to have the 9x squared over, I'm going to divide by a 6x squared y squared. Still have the cosine of 2x squared y cubed. And then I'm going to have minus 4xy cubed divided by that 6x squared y squared. And at this point, I would probably want to do some cancellations of the 9s and the x's. The 9 and 6 here will cancel by a factor of 3. Some x's will cancel. The 4 and the 6 will cancel by a factor of 2. Some x's and y's will cancel. Okay, I don't know why that stuff is not moving out of the way, so let's just make a nice little cluster up here on the top. There we go. So on E, same kind of thing, is I'm going to think of this as 3x to the 7th plus y squared raised to the 1/2. I'm going to think of this as the sine of y, the quantity squared, and then plus 10, 100xy. So I'm going to take the derivative of the left-hand side. I'm going to use the chain rule, so I'm going to get 1/2 3x to the 7th plus y squared raised to the negative 1/2. I'm going to do the derivative of the inner function, which is going to give me 21x to the 6th plus 2y, and then it has to slap on the dy dx, is equal to, take the derivative of 2 sine, so I'm going to have derivative of sine squared, so this is going to be 2 the sine of y multiplied by the derivative of the sine of y, which is the cosine of y, so that'll be the cosine of y, and then multiplied by the derivative of my angle, which is y, so that's a dy dx. All right, now I still have plus 100xy, so I have plus 100, the derivative of x is 1, so it'll be 1 times y, plus the derivative, and then it would be 100 times x, and then my derivative of y would be dy dx, dy dx. And of course from there I would collect up any term that has dy dx, and anything that does not have a dy dx would be moved to the other side. I would factor out the dy dx, and so from here it's just an algebra. If you want to go over this in class, we absolutely can. Otherwise, I'm just going to leave it. For f, I'm going to do something similar to the one I just did, is I'm going to rewrite this as x squared plus 5x plus 1 raised to the 1/3. I'm going to write this as minus the cosine of the sine of 3x raised to the 3rd. So dy dx, that is my right-hand side, is going to be 1/3 x squared plus 5x plus 1 raised to the negative 2/3 multiplied by the inner function derivative, which is 2x plus 5, minus, now I'm going to do the chain rule. The outer function is a cubed function. That's going to be 3, the cosine squared of the sine of 3x. Now I'm going to multiply it by the derivative of the next function in, which is cosine. So that's going to be negative sine of the sine of 3x. I'm going to multiply by the next inner function, which is the sine. So that'll be the cosine of 3x. And now I'm going to finally multiply by the most inner function, which is 3x. The derivative of 3x is 3. That did not need a dy dx, and in fact, the only one that has the dy dx was actually on the left-hand side. So f was just a bunch of chain rule, really. Had no needing to move dy dx to either side. It was already solved for y, so that was really nice. It's just a chain rule. Let's look at g. So with the g, I'm going to have 2/3 x raised to, remember I'm subtracting 3 over 3, so to be raised to the negative 1/3. Same thing with y, it'll be 2/3 down out front as a multiplier, raised to the negative 1/3. And then don't forget this one will need the dy dx. The derivative of a constant is 0, so solving for dy dx, I'm going to subtract 2/3 x raised to the negative 1/3 first, and then I'm going to divide by 2/3 y raised to the negative 1/3. So I'm going to have dy dx. My 2/3 will cancel. I'm going to have x raised to the negative 1/3 over y raised to the negative 1/3, which can be wrote as y raised to the 1/3 over x raised to the 1/3. And I can leave it just like that, or I can put y over x all underneath the cubed root. Either one of them will be perfectly fine. Now, up until this point where we're going to ask to do any evaluations, notice how on these evaluations are really nice. They give us the ordered pairs. They give us both the x's and y's. So that's really kind of nice. So let's go ahead and do the derivative first and then evaluate that. Now, when I am asked to find the equation of the tangent line, I typically do not simplify and solve for dy dx until I've done a back substitution of that ordered pair. So let's go ahead and just jump right into the derivative. So this is going to be 4x cubed minus, here's my u, here's my v, so it'll be minus 2xy plus 2x squared, x squared. The derivative of y is going to be just dy dx plus of the derivative of 4y, which is 4y cubed. Don't forget the dy dx. dy dx. The derivative of a constant is just 0. Now, it's not asking me for the dy dx. It's not asking me to find the derivative of y with respect to x, so I'm just going to do a back substitution. So I'm going to, everywhere I see x, I'm going to put in -1. Everywhere I see y, I'm going to put in 1. So this becomes 4 multiplied by -1 raised to the 3rd minus 2 multiplied by -1 multiplied by y, which is 1, plus x, which is -1 multiplied by dy dx. I'll do this in green now, dy dx. And then plus 4, y happens to be 1, and I used red for y, so I have 1, raised to the 3rd power, and then I have in green my dy dx is equal to 0. So I end up doing 4 times -1 to the 3rd power is -4. So I have -4 minus 2 times -1 is -2. This negative is going to pull through, so it becomes +2. So plus 2. This negative and this negative will cancel out, so I have just plus dy dx plus dy dx. And then I'm going to have 4 multiplied by 1 dy dx. So I end up with 4 plus 4 dy dx is equal to 0. All right, so I have -4 plus 2 is -2. I need to bring that to the other side. So I end up with 2 on the right-hand side. So I have 2. I don't know why I got rid of that, so 2. And then here I have 1 dy plus 4 more dy, which is 5 dy dx. dy dx. Solving for dy dx, I get dy and dx is going to equal 2/5. Now that doesn't answer the question. The question is, find the equation of the tangent. So my equation of my tangent line is y is equal to my slope, which is 2/5, x minus my x1 plus y1. And all of that work just to get that answer. All right, So I'm going to erase this so I can have space to do my next one. So for B, I already have my ordered pair 1, 1. So I have the derivative of x cubed, which is 3x squared, plus the derivative of y cubed, which is 3y squared. Don't forget the dy dx. dy dx is equal to, here's my u, here's my v, so I have to use the product rule. So it'll be 2y plus 2x dy dx. So that's the derivative of y. Now I'm going to evaluate this at the point 1, 1. So everywhere I see an x or a y, replace with 1. So this is just going to be 3 plus 3 dy dx is equal to 2 plus 2 dy dx. I'm going to subtract 3 from both sides. I'm going to subtract 2 dy dx's. So I end up with dy dx is going to be equal to -1. So my equation of my tangent line is y is equal to -1, x plus 1 plus 1, using these ordered pairs, this slope, and that is my answer for B. Taking a look at C, I'm going to do the same kind of thing as I'm going to do the derivative, and then I'm going to evaluate. So I'm going to take the derivative of the sine of y, which is going to give me the cosine of y multiplied by the derivative of y dy dx, which is then going to be equal to 5, or excuse me, not an equal sign, it's just going to be the derivative of 5x, which is plus 5. And then on the other side, I'm going to get 2y, and then the derivative of y is going to be dy dx. All right, so I'm going to go ahead and subtract, well, actually, let's do the evaluation. So the cosine of pi is -1. So it'll be -1 multiplied by dy dx plus 5 is equal to 2. My y again is pi, so 2 pi dy dx. Adding dy dx to both sides and dividing by what the coefficients would be. So I have 5 over 2 pi plus 1 is equal to dy dx. So dy dx, dy and dx. So my equation is going to be y is equal to 5 over 2 pi plus 1, x minus pi squared over 5, which is, and then plus pi. And so there is the equation of the tangent. Now, what happens if I'm asked to find the second derivative? Well, this is a little bit more involved. So I'm going to scroll on in here, 1, so that I have space, and 2, so I can see what I'm doing. So I'm first needing to find the first derivative. So I have 4x plus 2y dy and dx, which is equal to 0, because the derivative of constant is 0. Now, I need to solve for dy dx. So dy dx is going to be equal to -4x over 2y. In other words, I have -2x over y. Now, I have to do the second derivative. So I'm going to do dx of dy dx, which is, I'm going to use the quotient rule. So this is my u, this is my v. The derivative of the u, the numerator, is just going to be -2 multiplied by my denominator, which is y. And it's going to be minus. So I'm going to have the derivative of the denominator, which will have a dy dx, multiplied by my numerator, which is -2x, all divided by my denominator squared. This is why we have to take the moment to solve for dy dx, because d2y over dx2, the second derivative, is -2y plus 2x dy dx over y squared. So we have to go back to what dy dx was. Dy dx was negative 2x over y, and that's what has to go there. Dy dx was negative 2x over y. This is my replacement for dy dx. It is my first derivative. So then this is going to be equal to, I'm going to multiply everything by y because I can't have a nested or complex fraction. So I'm going to have negative 2y squared minus 4x squared all over y cubed. And that is my final answer. So that was a little weird, wasn't it? We had to first solve for dy dx, and then we're going to take the derivative. After I take the second derivative, everywhere I see dy dx, in the second derivative, I replace with what I found dy dx to begin with. And then I did some cleanup algebraically. Let's do another example. Let me move all this stuff over to the other side, and let's do another example. Once again, I'm just going to cluster all that stuff way up there. Okay, so this will give me this space here. I'm going to have 4x cubed plus 4y cubed multiplied by dy and dx, which is going to be equal to 0. And dy dx is going to be equal to negative x cubed over y cubed. Now I'm going to do my second derivative. And d2y over dx2 is going to be equal to, this is my u, this is my v. It'll be the derivative of my numerator function, which will be negative 3x squared multiplied by y cubed, minus the derivative of my denominator, which is going to be 3y squared dy dx multiplied by my numerator, which is a negative x cubed, all divided by y cubed squared. Now, this will be equal to negative 3x squared y cubed minus becomes plus 3x squared y squared. I have to replace this dy dx with this. So that then becomes, my replacement is negative x cubed over y cubed, all divided by my y to the 6th. And then, of course, I'd take that extra step to clean that up algebraically. Let's take a look at my last example here before we look at determine the slope in the next part. So I'm going to take my derivative of sine, which is cosine of x, plus, this is a product rule, here's u, here's b, so it's going to be plus 2xy plus x squared, and then dy dx, dy dx is equal to 0. So moving everything that's appropriate to the other side, I'm going to have, and do division, so I'm going to have negative cosine of x minus 2xy all divided by x squared is going to be my dy dx. When I'm ready to do the second derivative, d2y over dx2, I'm going to have the derivative of the numerator, derivative of negative cosine is negative sine, so it'll be sine of x, minus, and I'm going to have the derivative of 2x, which is just 2 multiplied by y, and then it'll be plus the derivative of 2x multiplied by dy dx, the derivative of y is dy dx. That is the derivative of the numerator that needs to be multiplied by the denominator, which is x squared, and then minus derivative of the denominator, which is 2x multiplied by the cosine of x minus 2xy, all divided by the denominator squared, all divided by x squared squared. And then, as you know, at this point, I do need to replace this xy, and I'm going to replace this xy with this entire thing, and it's going to go in right there. The dy dx gets replaced with that. So that's how you do second derivatives. You have to solve for the dy dx to be able to actually find second derivatives. Now they're asking me to determine the slopes. So the difference between this one and the one I did before is I don't have to make that extra step and find the equation of the tangent. It just is asking me for the slope. So once again, I go right to my derivative of x raised to the 2/3. So that's 2/3 x raised to the negative 1/3 plus 2/3 y raised to the negative 1/3 dy dx is equal to 0. And I am not going to simplify this. I'm just going to go ahead and put in 1 in the appropriate places. And so I'm going to have 2/3 1 raised to the negative 1/3 plus 2/3 1 raised to the negative 1/3 multiplied by dy dx. And this equals 0. Solving for dy dx, because that's all they want me to do. So dy dx evaluated at 1, 1 is going to be equal to, if I subtract 2/3 and then divide by 2/3, I'm going to get -1, and this is my final answer. Let's take a look at B. Again, I'm going to do my derivative. So I have 2/3 x plus y raised to the negative 1/3. The derivative of my inner function is 1 plus, and then the derivative of y is dy dx. On the other side, I'm just going to get dy dx. Then I'm going to go ahead and put in wherever I see x, I'm going to put in 4. Wherever I see y, I'm going to put in 4. So I have 2/3, 4 plus 4 raised to the negative 1/3, multiplied by 1 plus dy dx. Which is going to be equal to dy dx. So 4 plus 4 is 8. This is the cube root of 8 is 2. It's in the denominator. So that's going to be 2. That is going to be 2 over 3 multiplied by 2. So that thing is all equal to 2. Multiplied by 1 plus dy dx, which is equal to dy dx. So I end up with 1/3 plus 1/3 dy dx is equal to dy dx. I'm going to subtract 1/3 from both sides. Excuse me. I have 1/3 is equal to 2/3 dy dx. Divide both sides by 3/2, or divide both sides by 2/3, which is multiplying by 3/2, which gives me 1/2 is equal to dy dx. So for this one, dy dx evaluated at 4 is simply going to just be 1/2. And that's my answer for that one. Now let's take a look at this next one. Let me erase all of this so I can have some space. Looking at this example, I have to use the product rule, where this is u, this is v, and I'm going to do again, this is a new u, this is a new v. So the derivative of my first uv would be just y raised to the 5/2 plus x multiplied by 5/2, y raised to the 3/2, dy dx, plus 3/2 x raised to the 1/2 y, plus x raised to the 3/2, and then the derivative of y is dy dx, which is equal to the derivative of the constant is 0. Now I'm going to go ahead and put in 4 and 1 in the appropriate places. So I have 1 plus 4 multiplied by 5/2 multiplied by 1 dy dx, plus 3/2, and then 4 raised to the 1/2 multiplied by 1, plus 4 raised to the 3/2 dy dx, which is equal to 0. Okay, and so I'm going to get 1 plus, this 4 and 2 will cancel, so I get 10 plus 10 dy dx, plus the square root of 4 is 2, so just 3, plus the square root of 4 is 2, cubed is 8, and dy dx is equal to 0. Adding up dy dx is moving the 1 and 3 to the other side. I'm going to have 18 dy dx is equal to -2. So when I get totally done, dy dx evaluated at 4, 1 is equal to -1/9. Okay, so let's take a look at normal lines. What is a normal line? When I have a line that is tangent to a curve, then we know it's just barely touching a curve. So say we've got this equation and here's my curve. Now, if I said right here, I'm going to draw this tangent line, I'm going to just touch it and I have some slope. If I want the equation of the normal line, that means that, I'm going to do this in green, the normal line is going to cross through that point and it's going to be perpendicular to the tangent line. So the green is the normal line. So if I want to find the normal line or the equation of the tangent line, all I have to do is find the derivative, and all I have to do then is do the negative reciprocal of the derivative, and that will give me the slope of the normal line. The point is still the same. So this is what I know. If line L has a slope of m, and line L2 has a slope of -1/m, then line 1 and line 2 are perpendicular. Okay, so for this, we're asked to find the equation of the normal and the tangent lines. Now, what I'm going to do is I'm just going to give you the equations of the tangent line and then just, well, I'll do the, yeah, never mind. I'm just going to do the first one and then I'll let you all do the rest of them. So the derivative of 4x is derivative of x to the fourth is 4x cubed, which is equal to 4x plus 4y, then dy dx. Now this dy dx is going to give me the slope of the tangent line. So I'm going to evaluate this at 2, 2. So I have 4 multiplied by 2 to the third, which is equal to 4 multiplied by 2 plus 4 multiplied by 2 dy dx. All right, solving for dy dx. So dy dx is going to be equal to, I have on this left-hand side, I'm going to have 4 multiplied by 8, which is 32, minus 8, which is 24, divided by 8, which is 3. So this is 3. Now the equation of the tangent line then is going to be y is equal to 3 x minus 2 plus 2. This is the tangent. The normal line, will be y is equal to -1/3 x minus 2 plus 2. So the normal line is just going to be the negative reciprocal of the slope of the normal line, I should say. The slope of the normal line is just going to be the negative reciprocal of the slope of the tangent line. I want you to go ahead and pause it and do B and C on your own, and then come back to me and see if you're getting the same answers. Welcome back. Hopefully on the first one, when you evaluated that first derivative, dy dx at 2, -1, you got 14/55. That means the slope of the normal is going to be positive 55 over 14. And of course, the slope of the tangent for the second one is 1/3, so the slope of the normal would be -3. And then from there, you all can find the equation of the tangent line. This example, we're asked to find the lateral surface area of the radius r and its height h. Is the area is pi r multiplied by square root of r squared plus h squared. Find the derivative of r with respect to h with a lateral surface area of 100 or 1500 pi centimeters cubed. Evaluate this derivative when r is 30 and h is 40. Okay, what is this asking me to do? So I'm going to find the derivative of this function with respect to r or h. So I'm just going to jump right in and say dA dH is equal to pi derivative of r, which is going to be dr dH, multiplied by the square root of r squared plus h squared, plus, now I have to do, this is u and this is v, plus I'm going to have the derivative of the square root, so it's going to be 1/2. And then I'm going to have r squared plus h squared raised to the negative 1/2. And then I'm going to do the derivative of the inner function, which is going to be dr, it's going to be 2r dr dh, 2r dh, because I'm doing it with respect to h, so dr dh, plus 2h dh, and then multiplied by my u, which is pi r. Okay. So now what? Well, you're probably wondering, why did I do it all? Why did I do a dh? Well, that's because I'm finding the derivative of a with respect to h. I'm finding everything with respect to h. So wherever I have a variable, I'm going to do it with respect to h. Now we know that dh will be equal to 1, so I didn't really need to write that there, but I didn't want to not write that there because it would have been confusing as to why that wasn't there. But it really is 1. Now I'm going to go back and I am going to put in everything that I know. Find dr dh for a lateral surface area where the area is this. So that is my dA dH is going to be 1500 pi. And I have pi, my dr dH, and then I have an r of 30, so I'll put 30 squared plus 40 squared plus 1/2. My r squared is 30 squared plus my h squared, which is 30 squared, raised to the negative 1/2. And then I have times 2 multiplied by my r, which is 30. And then I have dr dh, which I don't know what that is. That's what I'm trying to find. And then, let me see. This is in parentheses. And then plus 2, my h is 40 at that moment in time, multiplied by pi, and then my r at that moment of time was 30. So the only thing that is different from this one than when I did previous ones is here's an application. I'm still chasing my dr dh. So I would distribute as appropriately and solve for dr dh as appropriate. And that's it. And that's actually going to lead us into 4.1, which is related rates. We'll go over any questions that you have in class. And I know this is kind of a long video and there's a lot of algebra involved. So let me know if you have algebra questions or if you have derivative questions. Otherwise, we will see you in class. Have a great